Okay, so should I just start? Or...
check if he opens the record.
Hi everyone, this is Eric Cambria from the Kindi Center of Computing Research. I mean, I'm here right now, but I'm from Nanyang Technological University in Singapore. And today I want to talk to you about AI and deep learning. So I just want to uncover some of the uh, models that people are using today when they do AI. Before that, I want to share with you this link. So if you want to know more about who we are and what we do, you can check out this link. We are a group of 20 people based in Singapore. So AI today is impacting society in many ways. One for all is the discussion about how many jobs can be replaced, but this is not something new. These things have happened in the past, in the history of humanity, with the revolution, agricultural revolution, industrial revolution. So there's many things to discuss about this, but today the focus is more on these models. But if you're interested in this, you can check out this recent report from IMF that talks about AI preparedness, how different countries, different economies are prepared for the potential changes in society that AI can bring. Before I start, I want to make clarify some terminology. So today you see these three terms: AI, machine learning, and deep learning used as synonyms, but in fact, deep learning is just one part of machine learning, because besides deep learning, machine learning also have other algorithms like SVM, for example, or feed-forward neural network. And then these both are sub-part of our AI, artificial intelligence, because besides sub-symbolic AI also have the symbolic AI, which can be semantic networks, for example, or ontology, or knowledge graphs, and so on. So before I start talking about neural networks, I want to briefly define some of the limitations of today's AI. One is dependency, the fact that the training data that we use to train a neural network can affect how well they can perform. Consistency, the bigger these neural networks become, the more difficult it is to understand what's happening in them, and sometimes you just change a few parameters and things work, but you don't know exactly why. Reproducibility, also a problem today, because it's not easy to replicate exactly the conditions to get certain results. And finally, transparency. Most of these tools that we use today are black boxes. You don't really know how certain decisions are taken. So there are different kinds of learning here. I put some for you guys to check out. I also put some short definitions so that you can see what each type of learning is doing. In general, deep learning is focusing mostly on inductive reasoning, but then there are other kinds of reasoning, like deductive or abductive reasoning, for which you need different techniques, like symbolic AI, for example. Few shots and zero shot learning also very popular today, as well as prompt-based learning, which uses masks to learn things that are very useful, for example, for large language models and systems like ChatGPT. So the big question today is, what is a neural network? I'm sure you've seen this model before. Neural network is a node made of many nodes linked by edges. But what each of these nodes does exactly? So if you just have one node, basically what this node is doing is just to decide whether the signal is passing or not, if a certain threshold is passed or not. So that's what you do when you do training. This dotted line that you see here on the right is something that you have to learn by training the network. Then once the threshold is set, depending on the input, the neuron can become active or not. So in this example, the input is 6, so the threshold is there at maybe 4.5, so the neuron becomes active, which means that the the signal is passed on to the next neuron. So what happens if you have two inputs instead? Let's say that besides temperature, we also want to measure pressure. Then instead of working on one line, you're working in a two-dimensional space. And this line now, this threshold now becomes a linear separator between an active area and an inactive one. When you add more stuff, you go in 3D, and this linear separator becomes a hyperplane, but the concept is still the same. Also, when you keep adding more dimensions, for us humans, maybe not so intuitive to understand what it means to work in more than 3 dimensions, but it's no problem for a computer. The interesting thing happens when you start adding more neurons. Then you start finding the non-linearities of the vector space by intersecting more of these hyperplanes. So here's actually the magic of deep neural networks. They are very good at segmenting the space into different pockets that you can use for classification, pattern recognition, or even to predict the next word. So one question that may arise now is what's the big deal now with neural networks? Neural networks have been around for so many years, so why now have they become popular again? The big reason is this: in the past, we used to have to define what are the features that we need to look for. For example, to recognize a car in an image, I need to specify that I need to look for the wheels, for the windshield, and whatnot. Now, deep learning doesn't need that. It can learn these things automatically from data. This is good because you don't have a human anymore. You don't have to pay someone to do that work anymore, but this also stripped us of the decision to make on which are the important features that I want to take into account. So there's many ways you can visualize this. It's basically a matrix with weights that define how much information is passing through different nodes. So you can see this as a network or as a matrix, as you see here. This matrix that you see many times when you study neural networks in books is the representation of this graph here. So let's say you have flatmate that cooks apple pie, burger, or chicken, and when it's sunny, it cooks apple pie, and when it's raining, it cooks burger. How can I implement this? How can I build a system that does this for me? The first thing that I need to do is to define a vector for each of these objects that I just mentioned. So this is very important to remember. We'll come back to this later. So these I represent. What I know about this food is much more than just these numbers, but I have no other way to represent these things for a neural network but to use numbers. So if I have a system, this is what is expected from my system. Given this input, I want this output, and when it's raining, I want to get the vector that corresponds to burger. So actually, this is just a multiplication of matrices. So what you could also do as an if-then-else encoding in terms of matrices, this is what happened into a neural network. So in this, if you want to see it from a graphical point of view, this is what happens here. I get as an output 1, 0, 0, which is the vector corresponding to the apple pie. So I use that example I'll come back to later to explain recurrent neural network. The problem with feed-forward neural network, which is the neural network that we've just seen, is that they don't model very well contexts. So, and they suffer from many issues like the exploding or vanishing gradient. But the biggest problem was that they were not able to model context. Later, people came up with the idea of convolutional neural network. LeCun actually came up with this back in the 1980s, but then back then the technology was not good enough to implement this. Later on, 2013, Mikolov came up with the idea of using this sort of sliding window to take into account context. This is valid both for images, so pixels, and surrounding pixels, but also for text. So if you are interested in how a convolutional neural network works, you can check this out. I don't have enough time today to explain how that works, but mostly is about max pooling operations. So you're just squeezing data into smaller slots in order to compress the representation of this data. And word embeddings is actually an old idea that existed even before deep neural networks. We were also using word embeddings to represent affective concepts in a multidimensional vector space. The news is that now, first, you can have, if two people are using the same set of word embeddings like word2vec, now we both have the same representation for that concept instead of having one made up like the 010 that I made up before. And most importantly, now we have we can take into account context. What is context? To put it simply, is just given a word, I look at the word or words that come before that word and the words that come afterwards. So all these, even the latest and most advanced technology for large language model, generative AI, what they're doing actually is just this. They are just very good at taking into account this joint probability, like having a dynamic sliding window that look at different contexts from sometimes from left to right, but sometimes also from right to left. What's cool about these word embeddings that's done the AI world before is that they are also encapsulating some semantics. So one popular example before was that if you take the vector of king and subtract the vector of man, you obtain a new vector that more or less is similar to the vector of queen minus the vector of woman. So this gives the idea that they also encapsulate some semantics, not just syntactic. Here in the next few slides, I put a brief history of the different types of word embeddings from word2vec, which was the first, to BERT, the ones that everybody is using now, which is based on the transformer architecture. So you can maybe check this out on your own if you're interested. This was the very first by Google, based on Google News, and it's based on that joint probability that I mentioned earlier with two different training methods. One is continuous bag of words and one is skipgram. Then came GLOVE, which was more powerful because it looked at also the frequency of the co-occurrence of these bits and contexts. Later, fast text by Facebook also look at not just words as a whole, but also add characters, add letters, for example, to take into account prefixes and suffixes. Then Elmo was extremely popular because it was a contextualized word embeddings. So if you ask for word embeddings of the word stick, for example, it would change depending on the sense that the sense of the word stick. So depending on the context mostly. Finally, BERT is the state of the art now because it can better model context by using attention model and masking, but most importantly because it can be parallelized, thing that recurrent neural networks are not really good at. So this is the family of BERT. There are many different versions of BERT, and there are many more new coming up every couple of months. Before I talk about transformer, I want to briefly talk about recurrent neural networks, which were also very popular for a while. This is the recurrent neural networks were working very well thanks to this feedback loop, which can be seen as a sort of back propagation. So if you use the thing that they were really good at is to model sequences. So here, let's take back the example of the housemaid that is cooking, and he cooks different foods in a different sequence. So the recurrent neural networks also take into account of what food was cooked before. So this is what recurrent neural networks are good at, because they don't just take a decision based on an input, but also based on a previous output, exactly. But this is no different from making some multiplication of matrices. So how do we model this? This is slightly more complicated than before, but not that much different. We have a bigger matrix that we can conceptualize as two matrices. So when we do the multiplication, we obtain two kinds of information, the one for the same day and the one for the next day. We have to encode somehow two states, and that's one way to do it. And the same we have to do for the weather, since the condition is also what food is cooked on which day. So let's take an example where yesterday apple pie was cooked and today is raining. What is the food that is going to be cooked today? I simply sum up the vectors that represent those concepts. Then I have to do some tweaking with the output because I don't have anything that corresponds to 1 to 1. And then in the end, after I sum up the two parts of the matrix, I obtain the output that is 0, 1, 0. So this is just a simple, very simplified version of how recurrent neural networks work. You can maybe find more information on Wikipedia or on YouTube about how recurrent neural network work. But actually, maybe you don't need to because they are already kind of outdated. People stop using recurrent neural networks, even things like LSTM that has been very popular for many years. Why? Because then they struggle with large sequences of text, with long sentences, for example. And most importantly, they were very difficult to parallelize. So next came the sequence-to-sequence model, which is very similar to the game of Pictionary. You have to build a compressed representation of a concept from an encoder point of view, and then a decoder needs to decode the meaning of this. So it's a bit like playing Pictionary. You have an idea, a concept that you have to draw, visualize, and then a decoder needs to guess what is the compressed information. So the hidden states that go between an encoder and decoder that mostly are used they can be used, the primary application is a machine translation, is a sort of Rosetta Stone that the decoder and that encoder and decoder use to communicate. So in the sequence-to-sequence model, bit by bit, I'm looking at the sentence, and as I go through the sentence, I have these hidden states that I pass between encoder and decoder, the context, basically. I have to provide context to have a better translation. That's why machine translation today it's so much better than before, because I don't translate word by word. I take into account the context of the sentence, the words that come at each stage before and after the word that I need to translate. So again, you can look this up if you are interested in the technical details. Here, mostly I want to show you that in the end is only a very good way to create a mathematical model of a sentence based on context that once again we define as things that come before and after the target word. So it's once again nothing but a sliding window that goes through the sentence. Here you see another example where the encoder also have its own hidden states, and after it goes through the sentence word by word, it passes these hidden states to the decoder, which on its turn has to do the same in a reverse engineering for the other target language. Here in the example we are using is from French to English, and as you can see, the word that make up each sentence can be different. It's not that it's the same number of words. So maybe I'll skip this once again. These are the technical details of how the sequence-to-sequence model works, but it's interesting to see how this works, to understand then later how large language models came about. It's the way generative AI works is also based on very similar mechanism where you look at the training data, which word comes after another, and what's the best word that comes given the past conversation. And this is enabled by transformers, which have the key novelties of transformers are the key point that made transformers so popular is that they can be parallelized. So we can throw as much computing power as we can to improve the performance, but also the fact that they introduce positional encodings, which is an old concept in information retrieval that takes into account the position of each word inside the document. Attention, very important, is deciding at each stage of the machine translation, for example, which part of the sentence is important to take into account, and also self-attention, which is not just an attention based, let's say, on the training data, but also on the sentence itself, which can be useful, like we see here in the example, to resolve pronouns, for example. What's the it in the sentence? I need some self-attention mechanism to better understand what to replace it with. So again, I'll spare you the details. You can check how exactly the attention mechanism works and how to build a transformer from scratch if you want. There are interesting tutorials that you can find online, and then later at the end I also have some links that you can use for finding more information about this. But yeah, the thing I want to leave you with is that transformers, no matter how powerful and good they are only good usually they are optimized for a downstream task. So I wouldn't go as far as saying that even though they have human-like accuracy on some tasks, they are emulating human intelligence. In fact, we may still be light years away from emulating the neuroplasticity of the brain. Even the biggest of the deep neural networks that we have today is still nothing compared to the complexity of the brain. There's still many limitations that we are yet to solve, even like when you talk about word embeddings. What are word embeddings? Are just vectors. And so for a large language model or for a system like ChatGPT, words are just a sequence of letters and nothing more. They're not really grounded anywhere. So this is the problem. Also in the examples that we used before, all those concepts that we mentioned, we represented them as vectors, but then of course they, in our mind, they are much more than vectors. We associate them with some emotions, with some taste, with some smell, with some past memory that we have. So we're still far from actually emulating the cognitive processes that go on in our mind when we communicate with each other or when we read text. So that's why in my group we focus not just on deep learning, but which are categorized as sub-symbolic algorithms, but also symbolic. So this can be called like hybrid AI or neurosymbolic AI. I have a video on this that I just posted as a labcast. It's called the 7 Pillar for the Future of AI. You can just Google this to find more information about this, to read the paper or to watch this video. And here I also put some links for you to check out if you want to, let's say, learn deep learning from scratch. These are some useful links that you can use for resources and videos, or there's a course from Stanford that really teaches you how to do natural language processing with deep learning from scratch. So that's pretty much it. There's some of the umbrellas of research umbrellas that we would be happy to work with any of you. This is something that I also discuss on that YouTube videos on the 7 pillars that I mentioned earlier. And you can find this video on our YouTube channel. You just have to search ScientificNet, and we also have, if you want to keep updated, we also have a account on Meta and on X. And here I also put some links for some free resources that you can download. There's also free code on our GitHub and also APIs in different languages that you can use for free. On our website, you also find some avenues for sending your papers. There is this special section on cognitive computation and some call for papers on IEEE intelligence systems and other journals. And then last thing, this December, we're coming back to the Middle East. Abu Dhabi has the ICDM conference, International Conference on Data Mining, in which we had for more than 10 years our workshop series on affective computing and sentiment analysis. So if you want to meet again, you can see me there. Thank you for your attention. That's all for today. If you want to, if you have any questions, please feel free to contact me at the email that I provided in the beginning, eric@centik.net. Thanks for watching and see you next time.